So page 76, number 55. I have a graph on it. Okay, so 55, so page 76, number 55. Alright, so this is asking you to create a graph. I do like this type of question. I probably expect to see this type of question on a test. So what it says is, sketch a graphing function y equals f of x that satisfies the stated conditions, include any asymptotes. So it says, the stuff that we're given, it says the limit as x approaches 1 of f of x equals 2. The limit as x approaches 5 from the left, f of x is equal to infinity. The limit as x approaches 5 from the right, the f of x is equal to infinity. And the limit as x approaches infinity for f of x is equal to -1. And the limit goes up. As x approaches -2 to the right of f of x equals -infinity. And the limit as x approaches -2 from the left, the f of x equals infinity. And finally, the limit as x approaches -infinity, f of x equals 0. Alright, so what this is asking me to do is just create a graph, any graph. It doesn't take, there's multiple ways to answer this. And you have to create a graph where it has all these problems. Alright? So what I would start off by doing is just, first of all, drawing my x and y axis. Yes, alright, so first thing that I'm doing is I would see what points I need. Alright, I have 5, I need to put 1 on there, I need to put -2 on there, and that's it for the x points, like other than infinity and -2. So I'm gonna put, I have 1, 2, 3, 4, 5, I'm gonna put 6, 1, 2, 3, 4, 5. Alright. So I know that as the limit as x approaches 1 of f of x equals 2. Okay? So I know what that tells me is that the limit as x approaches 1, it exists and it equals 2. That means at x equals 1, so right here, this function is approaching the y value of 2. I'm just going to put a point there.
Is that for the first one?
Yeah. And it could be an open circle, so it could be a hole, or it could just be a point, but I'm just going to put a point.
What was that, 1, 2?
Yeah, because it says, as x approaches 1, the y value is approaching 2. So I know it has, I know it's approaching 2 to the left and to the right, because it says that the overall limit is 2. Alright? So I know that right here it's doing something, maybe something like this, I'm not sure. But now, we will just leave that point there. It then says, as x approaches 5 from the left, alright, it approaches infinity. As f of x approaches, or as x approaches 5 from the right, f of x approaches infinity. When I have something approaching infinity, that means that there's an asymptote there. Alright, so that tells me that there's a vertical asymptote at x equals 5. So 1, 2, 3, 4, 5. I know that there's a vertical asymptote at x equals 5. And what I know is that on the left-hand side of it, the y values are going towards infinity. And on the right-hand side of it, the y values are going towards infinity. So I know that this is going to be, I know that this function is going up here and up here. Does that make sense?
Yeah.
So, it then says the limit as, let's look at -2 first. Limit as x approaches -2 to the right of f of x equals negative infinity, as it approaches to the left, it equals positive infinity. So when I have limits that equal positive or negative infinity, that again tells me that there is a vertical asymptote. Alright, so if there's a vertical asymptote at -2.
Did we do a problem like this two days ago?
Possibly. Actually, I don't think we did one exactly. We might have done something similar. So I know on the right-hand side of -2, it approaches negative infinity. Alright? And on the left-hand side of -2, it also it approaches infinity here. Right? Now, final thing I know, let me draw this. Alright, so the final two things that I have is it tells me as x approaches infinity, x approaches negative infinity. Alright, so when x approaches positive infinity, f of x is approaching -1. Alright, that means out over here, alright, this function is once it starts going out towards infinity, it is going towards. It's going really, really, really close to -1. It uses a horizontal asymptote at -1 on this right-hand side of the line of infinity. So what I know is, at some point in time, there's going to be that horizontal asymptote that sort of comes out this way. All right? And then I look over here, it says that x approaches negative infinity, there's a horizontal asymptote at 0. That means I know that right here is that horizontal asymptote out here. Alright, so at that point, I've taken care, I had everything sort of labeled out, I had everything sort of drawn in. Now I just need to sort of create my graph. Alright, so first thing I know is that this side over here starts up here, and then it's going to look like this. Alright, it's going to go out towards 0. Alright, now over here, this graph has to start down here towards negative infinity, has to end at positive infinity, but also has to pass through this point at 1, 2. So it doesn't matter what it does. You can make it do whatever you want it to, but typically if I over something like this, I come up like that maybe. Okay? Not 100% sure because we don't know what the graph is, so we can't say 100% what it looks like. And then over here, I come down. And go out, and it's going to just get really close to -1. Make sense? Again, really the only thing that could look different is that middle part. You can make it do different things. But it would look something similar to that. Questions on that? Alright. So, let's look at number 20. Hold on. Do that. So then, let's look at page 84, number 20. Alright, so page 84, number 20 says, it says, get f of x equals 3 minus x, and x is less than 2, and 2 when x equals 2, and x divided by 2 when x is greater than 2. Okay, and it says, part A, find each point of discontinuity. Part B, which of the discontinuities are removable, not removable. Give your reasons for your answer. Okay? So first off, piecewise function. Alright? What you want to do is you want to check to see what y value each of these are approaching as you get closer and closer to 2. Alright? So essentially what you're asking yourself here is you want to see if the right hand and left hand limits are equal, and also see if they are equal to the function value at 2. So the only point that we're really concerned about right here is x equals 2. So we know something's going on there. And in order to see if it's continuous or not continuous, what we need to do is we need to show that the left-hand limit of f of x is equal to the right-hand limit as x approaches 2 from the right of f of x. And we need to show that it's equal to f of 2. If all three of those things are equal, then we know that this function is continuous. If they're not, we have to figure out what type of discontinuity it is. So if you look at this, f of 2 is just equal to 2, because it tells us that when x equals 2, f of x is equal to 2. Alright, so we know that f of 2 is equal to 2. So that means that the left-hand limit and the right-hand limit have to be equal. To figure out the left-hand limit, we can just plug it into here. 3 minus 2, that's 1. Okay, so already we can see that that is not working out so far. The right-hand limit is going to be this function right here. We have 2 divided by 2, which is 1. Alright? So the left-hand and right-hand limit are the same, but they are not equal to the function value. So if you look at that graph, kind of what you would have would be something that looks like, I'm not going to draw it like so it's actually what it is, but it's saying that as you approach 2, well, as you'll see, we have 3 minus x, it would be something like, we have something like this. Alright, and then there's going to be, right here, that would be, there's a hole here. Alright, and then it's going to keep going maybe a little bit something more like this. And then its function value is right there. Alright, so what we can see just by graphing this is that it is a hole. Okay, and the way we know that there's going to be a hole is if the left hand and right hand limits are the same, they're equal. That means that discontinuity is a hole if there is one. Okay, if they're different, that means it's a jump discontinuity. That makes sense? So if the left hand and right hand limits are equal, hole. If there's a discontinuity, if they're not equal, it's a jump discontinuity. Okay? And so a hole is a removable discontinuity because we can fix it and fill it in. Alright? So this would be a removable discontinuity because it's a hole that we can fix. Make sense?
So are you getting plugged in 2?
All you do is you plug in 2 into each one of these. If the left hand and right hand limits are equal, the whole, if they don't equal the function value, they jump discontinuity if they're bigger. Alright? So, that being said, since you know the questions on homework, you can turn that in at the end of the class. And what we're going to do is, remember on...
Wait, you said that one was removable?
This is a removable, yes. Holes are removable. If you get a hole, it's removable. If it's a jump discontinuity, it's not removable. Not removable because you can't fill up a jump because there's more than one spot to fill up. Alright? So, what we've been talking about, alright, is continuity. We've been talking about limits. We've been talking about whether or not function is continuous or not continuous. Alright? And what we want to talk about now is writing what's called an extended function. Alright? Extended function means if we have a hole, okay, so you can only do this if you have a hole. If you have an extended function is what can we use to fill up the hole? That's what we're trying to figure out. what y value could we define, or what y value could we define for that pole that would allow this function to be continuous? Okay, so what we're going to look at here, and we're only going to look at this first equation. Okay, it says f of x is equal to sine 2x divided by 5x. All right, so what we're going to do here is, first of all, we have to make sure that there is a hole. Okay, never assume that there's a discontinuity if someone's asking you about a discontinuity. Always check it. All right, so just by checking this, we're looking at, we want to see if there's a hole or discontinuity at x equals 0. So if we plug in x equals 0, we're going to get sine of 2 times 0, which is 0. So sine of 0 is 0. 5 times 0 is 0. So if we plug 0 into both the numerator and denominator, you get 0 divided by 0, which tells you that there is a hole. So we know there's a hole. Now, we all know, what was the limit as x approaches 0 for sine x over x? It is 1. Good. All right, remember, it looks the graph looks something like this. It was like, all right, horrible drawing, but there's a hole right here, x equals 0. And obviously, since it's mudboard off a little bit, we need to align it. That looks like the Pac-Man goes. All right, so we know there's a hole there. Now, yeah. So we know there's a hole at x equals 0. So what we want to do is we want to fill it in. We want to make this function continuous. All right, and in order to do that, we need to figure out how can we define this function. All right. So as an example, because we know that the limit as x approaches 0 for sine x over x is 1, what we would do is to extend that function, to fill that hole in, is you go f of x is equal to, so you have sine x over x now. So it's equal to that when x is not equal to 0. Okay? Because it's undefined at 0. And then you say, and then here you said the limit is 1. So that hole is right there, is at 0, 1. So what we would say is it equals 1 when x is equal to 0. We can just define it. We're extending the function and we're defining that and saying, okay, now that function is continuous. Alright? So we're going to do the same thing over here. However, this isn't sine x over x, is it?
You need that right here?
No, I was just giving you an example of what that would look like. So here we're looking at f of x equals sine 2x divided by 5x. Alright? And we said, and we've talked about this, this is on one of your homeworks, where you had a bunch of like sine 3x over 3x and 3 over the limits are and whatnot. Alright? And we said that when this is the case, when you have sine of 2x, you need to have a 2x down there. So if we had sine, how is this numbers? So if you had sine 2x over x, at x equals 0, what does that approach? If the numerator is that 2x right here, and this is the 2x, what would that be? What would the limit be? And so the limit, we know the limit as x approaches 0 of sine 2x over 2x, you said we knew that equals 1. Alright? But so in this case, you don't have a 2x on the bottom, we have a 5x. So what we have to do there is we have to multiply. We get a little tricky. We have to say, okay, well, we have to multiply this by, we have to change this, but the only way we can change it is by multiplying it by 1. But to multiply it by 1, we have to get a little tricky. Alright, so we'd have to say, okay, well, we have to go, 2 over 2 times sine 2x over 5x. Alright? And then what that gives us is you get 2 sine 2x divided by 5 times 2x. So that is rearrange the 5 and the 2 for multiplication. Good with that?
Yeah.
Joe?
Why,
What?
actually,
Goes out.
why is that two X?
Huh?
Why is that two?
Why is this 2x?
Yeah.
Because 2 times 5 is the same as 5 times 2. So I just switched the order. Alright? So now, what do we see? Well, I have a sine 2x and a 2x here. So if I was taking the limit of that, alright, so the limit of that would be, remember, I could then take out, we have that constant rule that says I can take out the constant in the front. So that 2/5 right there. Remember that rule? Properties of limits? And we have 2/5 times the limit as x approaches 0 of sine 2x over 2x. And we know that this limit is what? 1, so we have 2/5 times 1, which is equal to 2/5. Alright, so we know that this function, alright, to define this, to write our extended function, we would have to say, okay, f of x is now equal to sine 2x over 5x when x is equal to, or not equal to 0, and is equal to 2/5 when x is equal to 0. That make sense? Questions? So the idea here, well, when x equals 0.
What is that more more? Is that supposed to be a comma?
Where? Here? Yes. So the idea here is, what you want to do is you want to figure out what is this function approaching, or what is the limit of this function as I'm approaching, in this case, 0, because I'm dealing with x equals 0. Alright? So all you have to do is really find the limit of this function, and then the limit of it is 2/5. So then you say, okay, well, I'm letting f of x equal this 2x sine 2x divided by 5x when x is not equal to 0. But when x is equal to 0, I know that function is approaching 2/5. So I'm filling that hole in. I'm letting it equal to, I'm saying this hole is now x equals 0, and we're saying that the y value is 2/5. We're defining it. Makes sense. Yeah?
But when you write, how much do you feel wrong?
What do you mean?
Like, you just,
Jumping around?
yeah.
So we went from here, here, there, there, full circle.
Weird.
Because I ran out, I said, I don't want to use forward that one. I guess I could have written it. Alright, so we're saying that, so another way you can say it, so you do all this, you get to the limit and say limit as x approaches 0 there is 2/5. So then you can just also say f of 0 is equal to 2/5. Alright, that way you don't have to write all that. We can say f of 0 is equal to 2/5. Because what the question is asking is, what value should be assigned to f of 0? Alright, so, cool? Does it make sense?
Yeah.
So what you do, you just find the limit at whatever x is, and then you say, and you take that and you define it as f of x is equal to, or f of whatever value that is equal to that limit.
So I would have to like that,
What, this?
because I don't know. Because I don't like
This?
that. Yeah, I don't like
No,
that.
you don't have to like that. You don't have to. Don't. Alright, so,
Oh, my God. Thank you so much.
you're gonna is that about?
Yeah.
This?
I'm just gonna go the whole problem.
I don't think it is.
Yeah, go on.
Yeah, it might be. Alright, so, first thing that we need to do, so what it's doing here is asking, what is the value here for, in this case, we're not looking at x equals 0, we're looking at x equals 3. Okay? How do I know?
Never mind,
Why? Did you figure it out?
never mind.
Yes, because if I'm looking at that, I see that if I plug in, 3 minus 3 would be 0. So that means that, let me check up here. So 3 to the third power would be 27 minus 7 to the 3 is 21. So 27 minus 21 is 6. 6 minus 6 is 0. So that's 1. Why are you plugging in 3? Because
Maybe it's equal to 0.
the bottom is equal to 0. Yeah, Michelle noticed that there was that whole part where you plug in 3 minus 3, so if I put 3 in for x, I get 0 in the denominator, which is bad. Alright, so 1 second. Do we do that? I can tell you what I'm doing. I'm doing syntax, I just did syntax division to figure out what I can factor out of this. So what happens here is, first of all, I need to figure out the limit as x approaches 3. Alright, so I want to figure out the limit as x approaches 3 of this function. Now, here, I know that in order to figure out that limit, I want to use substitution, but I can't use substitution until I get rid of this x minus 3. So what I did was I used syntax division, alright? So I know x equals 3 is a factor. I know why x equals 3 is a 0. So what I did was I did syntax division with 3 and this numerator, so we 3 and 1, 0, -7, and -6. So this is from 3 down. Bring the 1 down. 3 times 1 is 3. 0 plus 3 is 3. 3 times 3 is 9. -7 plus 9 is 2. 3 times 2 is 6. Which equals 0. So I know that this top part factors into x minus 3 times x squared plus 3x plus 3. X squared plus 3x plus 3. Alright. So the x minus 3's cancel out. I'm left with find the limit as x approaches 3 of x squared plus 3x plus 2. Well, at that point, I can just plug in 3. 3 squared is 9, plus 9, 18 plus 2 is 20.
Where do you get the x minus 3 from 1 time?
So what?
X minus 3.
Because I know I'm factoring, I do have to generate the x minus 3. So I know that this is going to factor, so I can factor x minus 3 out of here. And I use the syntax division to figure out what my remaining factor is. Alright. So then I plug in x equals 3 into here, to find the limit, I get 20. So that tells me that to extend this function, f of 3 equal to 20.
Oh, that was easy.
The only tricky part of that is that you have to remember syntax division, right? Which is fairly a straightforward process. I believe you guys probably remember that. How does that equal? We're talking 33, so I get 9 plus 9 is 18 plus 2 is 20. questions about that? Those are problems you're gonna be having from, 84 that you didn't have last night, 25 through 30, and whatever that other one was. So, So this one says, find a constant A such that f of x is continuous over the real. Alright? So what we know, we have a piecewise function here right now, right? So what it's saying is, we need to figure out what A is to make sure that this is a continuous function. Okay? So what that means is we need to find out, we need to figure out what the limit is of x cubed first. Alright? So we need to figure out what is x cubed approaching right now. So the limit, what is going on with this monitor? So the limit as, well, that actually, we just need to see what x, we just need to see, it says x cubed when x is less than or equal to 2. So really what we need to do, we're only concerned about this. The only place that we could possibly have a discontinuity is right here at x equals 2. So first of all, we know x cubed, when x is 2, that's going to be 2 cubed, which is equal to 8. Does that make sense? So that means that this function that looks something like this is going to be 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Here, something like this. Alright, we know it's filled in there. We know that this right here is equal to 8. Alright? So what we need to say is this. We need to figure out what A is. Make sure that this part right here is continuous up here. So ax squared at x equals 2 needs to equal 8. Okay, because the only way this is going to be continuous is if, the only way that this is going to be continuous is if there's not a jump discontinuity there. So we know this ax squared has to equal 8. So I need to solve, right? I know ax squared, that has to equal, well, actually, I know even more.
Wait, for the, graph real quick, did you just put like one?
1, 1.
You just put it there?
Well, it's because 1 cubed is 1, so that's how you know. So actually, I know even a little more. I know at x equals 2, okay, this needs to be equal to 8. So I have a times 2 squared is equal to 8. Alright? So, a, 2 squared is 4, so 4a equals 8. Divided by 4, I get a equals 2. So we're saying that 2 has to be equal to a. Alright? So really what this should be saying is 2x squared. And you can check your answer. Alright? If I plug 2 in here, does that give me, does this make that continuous? So if I plug in 2, I'm going to get 2 squared, 4, 4 times 2 is 8. So what I know is that this is approaching, it doesn't actually equal 8, because x is greater than 2, but it's right there, it would be approaching 8 in the right. Does that make sense? All you do is you figure out, okay, what is the function value at this point, wherever the equal sign is, and then you just take that same x value, plug it in, solve for a. This is a fun problem that's always on the AP test. They usually use like a variable k.
So it's a circle to a house around the.
No, it's not. The only thing I put building, or a circle there, is because this says x is greater than 2. So really, this isn't, like, I can't like really do x is equal to 2 here. But I know that when it's equal to 2 here, it's 8. And I know that I need to have it so that this limit, alright, whatever, that this limit right there is approaching 8, or approaching that value right there. Alright? So really, there would be a hole there if this just said less than 2. That doesn't say less than or equal to 2, there would be a hole. Okay? I believe you guys got a coupon right now. Alright.
Yeah, I want to begin.
Yep. So, the intermediate value theorem. Alright, we're not going to talk too much about this, but this is very important. You need to write this down. Alright? The intermediate value theorem. We're going to typically refer to it as IVT. Intermediate value theorem. This is going to come into play a lot later on. Alright, and I just want to touch base on this because it has something to do with what we've been talking about, which is continuous functions. Okay? So what it says the intermediate value theorem. If a function f of x is continuous over the closed interval a to b, then the function will assume every value, all right? And this is italicized. That's talking about y values. Okay? Every y value between f of a and f of b at least once in the interval a to b. All right? So again, if a function f of x is continuous over closed interval a to b, then the function will assume every y value between f of a and f of b at least once in the interval a to b. Okay. So what that's saying is, I have my not sure. If I have a function and have, let's see, a, b, and something like this. Well, and this is f of a, so f of a is right here. F of b, say right here. Let's just say f of a is, say f of a is 2. Let's say f of b is, say, 9. Alright? What it's saying is this. Alright? You guys all ready to pay attention to what I'm about to say without the knowledge? Alright. So what it's saying is this. If the y value at a equals 2, or if the y value at x equals a is 2, and the y value at x equals b is 9, it is saying that this function will take on every value between 2 and 9. It has to. Alright? It doesn't matter if it's a straight line. It doesn't matter if it is something like this. Alright? It is guaranteed that this function, if it's continuous, that it will take on every y value from 2, 3, 4.5, 9, 7.6, yes? 3.2, 4.9, pi, 87, divided by 90, 87 divided by 87? No, it actually wouldn't work. But you get the idea is every value between 2 and 9, every y value between 2 and 9, this function will take on that value, assuming it's continuous. Alright? I mean, that should make sense. Because the only way to get from 2 to 9, no matter what, is if you pass through 2, 2.1, 2.3, 2.4, 7.9, 6.2, right? That's the only way. Even if it's just a straight line, even if it's just a line that goes straight there, you have to pass through every y value between f of a and f of b. Make sense? Alright. And boom. So, next. So for that, guys, your guys' remaining homework from that page, right, is, let's say 84. So it is, your remaining homework is 25 to 30, 47, and 50. Alright, 25 to 30, 47 and 30. Those are the remaining problems on page 84 that you need to complete. Alright? Oh, all the time to get that done.
And as long as you want, Sarah.
Bro, what movie was we watching?
No, you ready? Alright. So, what we're going to talk about right now is rates of change in tangent lines. Okay? Now, here, what if I told you guys that the hardest that this is going to be is slope and limits? You know how to do limits. You've been knowing how to use slope.
I'm stuck at school.
Yep, there you go. Y2 minus Y1 over X2 minus X1. That's all you're doing.
Oh, I thought you were asking me the answer to that.
That is all you're doing. Okay? So we're going to talk about rate of change of a function. All right? So what we're going to do is we want to describe, graphically what we're going to describe the slope of a function. All right? So graphically, what are we finding? We're finding slope. Okay? And like I just said, you all know how to find slope already. You already know that. It's y2 minus y1. This is all y2 minus y1 over x2 minus x1. Alright? This is all we're doing. To find the rate of change, to find the slope, to find tangent lines. Nope, nothing.
No.
Rate of change? Nope. Anything here?
Are you going to write them here?
No. I just want you to think about it.
You mean there's something coming after?
Huh?
Oh.
There is, right there, grab it. Alright, so, rate of change of a function. Again, all we're going to be doing is we're finding the slope of a function. Now, typically when you think of slope, what type of function are we talking about? What? Linear. Alright, so here's the thing. We're not finding the slope of any linear lines anymore. We're finding the slope of functions that are curves. Okay, so you're going to have some curves up in here. Now, all that.
Shamar, stop saying that
So,
because she'll know it's done.
Shamar, this is what I want you to know. All we're doing this entire day is y2 minus y1 divided by x2 minus x1. But it's going to look a little different. It's going to be the exact same thing, but it's going to look a little bit different. It's literally the exact same thing, we're just saying y2 different and y1 different. So, oh, look, this looks like what?
Wait, that's X to my X1.
Yeah, this looks like what Akira just said. Okay?
What did yours,
She said that typically we know linear lines. You know how to find the slope of linear lines. Right? However, what if your slope isn't linear? Right? So, what we're going to do here, right, is we are going to, again, it is just still going to be y2 minus y1. Right? Look. Yeah, you don't have this graph. So, I use a second to draw that. Right?
oh, my gosh,
You think we should take what further?
Alright, so you have this. Now, what we're gonna do here, where'd it go? Alright, so what we have here, we're looking at this right here, and we have we're still gonna figure out the rate of change, alright, of this function the exact same way it is linear. What we're gonna do is we're gonna take, in this case, with y log. Alright, so, yes, it does. So we have this point right here, alright? And this is our A dot, that's when x is A, this is when x is B. Okay? So what we're gonna do is, in order to be a little bit more classy, be a little bit more calculusly, what we're gonna be doing is, instead of using this and finding the slope as y2 minus y1 over x2 minus x1, right, we're gonna find this as, we're gonna say the slope is equal to n, right, so the slope is equal to, now instead of saying y2 minus y1, alright, we have our way of notating this as, this is f of b, this is f of a. So what we're going to do is, this would be like our y2, so we're taking this and saying f of b minus f of a divided by b minus a. Alright, same exact thing. It is still, that fb is our second y value, f of a is our first y value, b is our second x value, a is our first one, or first x value. Alright? So that's the formula we're gonna use. Right? So what we're gonna do here, let's take this right here from there. Now, one thing that we can do is we can take we can always start from endpoint and go to our other point. Alright, so if we look at this, we have this function that looks like this. That's a quick one, that's not cool. Alright, so let's make this. Alright, so what we want to do here, okay, again, to find the average rate of change, we're just going to find the slope between 2 points. Alright, to find the average rate of change of this function, we're finding the slope of 2 points. Alright, or between 2 points. So, what we have here, this is our A. Alright, so this is our point A. This is our point B. And then we have f of B. And we have f of A.
Why do you?
What?
I didn't be over there.
It's a point on the graph, right? I could. We'll look at that in just a second. Alright? So, we go ahead and we're going to take a look at this. Alright? So we have, remember, our slope, or our average rate of change, is equal to f of b, which f of b would be what? 120. So 120 minus f of a, which is what? 0. Okay. And then we have b minus a, which is 10 minus 0. Now I do want to backtrack real quick, because I forgot to say something. This is distance versus time graph. Okay? And we are finding the average speed. Alright, it says find the average speed. Now here's the problem. We know this is the equation for average rate of change. Right? Not the average rate of speed. But what you need to start thinking about in calculus is that speed is talking about the average rate of change of distance. It's saying how fast do you travel over time. So speed is the rate of change in distance. All right, so what we're really finding when we're finding the average speed is the average rate of change in distance. Okay, so speed is the average, or the average speed is the average rate of change in distance. So what we're doing is we're finding that rate of change in distance. So what we do here, 120 minus 0 is 120 divided by 10, which is equal to 12. And what we need to make sure we do here is put our units. Because our speed, our average speed is not just 12, right? 12 what? Miles per hour? Miles per second? What would our speed be? Miles. That's meters. Right? N is meters. So it's 12 meters per second. All right? So that's our average speed of this function, right? Now here's my question. Is the average speed of our function 12 meters per second over this entire function? Sure. So you're saying that?
No.
What do you mean no, Kara?
That's between point A and
That's between point A and point B. And there are places where it's less than or more than 12 meters per second.
Yeah.
What do you mean, 5?
I was going to say 30 minutes, 5.
Okay, so where would it,
30 meters is constant.
so you, between what? Just at 5 seconds is less than 12? Or is it over
That,
3?
if you would do that, at that point it would be a different.
So I would have gone from what point to what point?
Can really off.
Okay, good. So let's look at this. So what we did is we found the slope between 0 and 10. So we found the average speed between 0 seconds and 10 seconds. However, if we look at it differently, all right, so if I take another line and draw it, I'm gonna have to, so if I went from 0 to 5, watch this, hold on, don't freak out, this bit. All right, so we go this, boom, and boom.
That was like the same.
So right there to there, we're finding the slope. Which slope is bigger, from 0 to 5 or from 0 to 10? Okay, good, 0 to 10. So here, the slope isn't quite as big. Now if I draw one more line, maybe
5, 10.
5 to 10, if it knew how to, like, you know, not get drawn here, obviously.
Oh, you did it say.
I'm about to punch something. About to get real. Alright, so,
Okay, bye.
I look at her like this right here.
I'm getting another couple. Which one?
Alright, so we have this bootleg, line right here, that apparently doesn't want to keep working for
Why are
me.
you yelling at us? We are only 4 of us in here.
So clearly, we can see that between 0 to 5, the average rate of change would be less. Between 5 and 10, the average rate of change would be greater than 12. Alright? We would calculate it the same way. You would just, so if if you went from 5 to 10, you would have your slope is equal to 120 minus 30 divided by 10 minus 5. You'd have 90 divided by 5, which would be equal to 18. Yep. Not too bad, right?
Nope.
Pretty easy. Well, I told you that's all you're doing.
You lied then.
I lied?
You said it was really hard. Oh.
Wait.
You probably believe the thing.
I think I did it.
It's okay. Twice. And he was just like, maybe you can scroll.
That's Alright, so let's look at this. Let's actually find the average rate of change for an actual function. Alright, we don't know what this function looks like. But we know we have a function. We want to find the average rate of change over this interval, 0 to pi over 2. Alright? So, real quick, someone explain to me what is our equation for finding the average rate of change?
Isn't that, wait,
Yep.
that would be minus f of a divided by b minus a.
Okay, so our b would be pi over 2. Our a would be 0. Okay, so all we're doing is we're finding f. So what we're doing is find f of pi over 2 minus f of 0 divided by pi over 2 minus 0. Alright? So, f of pi over 2 means we plug pi over 2 in. So sine squared of pi over 2 minus 0, or minus 1. Alright? So, f of pi over 2, I'm going to do this off to the side, is equal to sine squared pi over 2 minus 1. Alright? So, what is sine squared of pi over 2? We got to figure that out. Well, we know sine of pi over 2 is 1. So 1 squared would be 1. So 1 minus 1 would be 0. So this is so f of pi over 2 is equal to 0. I have f of 0 to figure out. F of 0 would be sine squared of 0 minus 1. So we know that sine of 0 is 0. 0 squared is 0. Subtract 1, that's equal to negative 1. So that's negative 1. So we have a 0, so f of pi over 2, which is 0, minus f of 0, which is negative 1. Alright, divided by pi over 2 minus 0, which is pi over 2.
Oh, that was great.
That's a nice line.
Actually, it's not that fun.
What, you a nerd and you like saying on this stuff?
Yep, I think it's pretty cool. So, 0 minus negative 1, that's going to be positive 1, divided by pi over 2. Alright, and that's the same as saying 1 times 2 over pi. Alright, because really it's saying 1 divided by pi over 2, so that's the same as multiplying by the reciprocal, 1 times 2 over pi. So your answer is 2 over pi. So, what that's saying is the average rate of change over the function sine squared x minus 1 from 0 to pi over 2 is equal to 2 over pi. That wasn't too bad, right? Mitchell, don't lie. Don't lie to YouTube. Wasn't that hard, was it?
I mean, I don't even know where we can go with now, so like,
Follow me on Instagram.
Oh, what'd you say? But, I mean, in all seriousness, guys, that wasn't that hard. The only really tricky part is remembering sine of pi over 2 and sine of 0. All you do is add and subtract, and then you do the division. Nope, it's not. No, it's not.
Yeah.
He has a bunch of bots following him. Alright. Bots. Alright. where it gets a little bit different. Hey, Michelle.
I'm ready.
Alright, here's where it gets a little bit different. Alright, what if we want to find instantaneous velocity? Meaning, I want to know the exact velocity at one point in time. I do not want the average. I want to know exactly the speed right here at this point.
So this is where we get that little piece of in there, we get it from the.
You mean the chairs? Yes, this is getting more into the chairs. Alright, when you push each other. Forward.
Yeah, I kind of figured that, but we just did average speed.
So, instantaneous velocity. You want to know the speed, velocity. You want to know the speed at the exact point. We don't want to know an average. Alright? So, what we need to do is we need to, first of all, so let's say we're looking at these graphs. We have two questions that we sort of want to answer here. Alright? Because if we can do this, we can answer these two questions. How do we find the slope of the tangent line? And how do we find the slope of the curve at a single point? If we can do that, we can find the instantaneous velocity. Okay? Any ideas of where we're going to be going? Of what we might need to use? So we're going to use slope. We talked about this at the very beginning of the year. This year. So like in August. That was the very first thing we talked about in this class. Limits. We're using the definition of slope and limits to be able to answer these questions. Alright? So, you have these two graphs right here. Alright? And what we want to do, what we know how to do, is we know how to figure out. Alright? Let's say we start at point A, and we'll say this. Apparently point B is up there. Alright? So that's how. So, this is B. Alright? So what we know how to do is we know how to figure out how to kill smart words. That's the next rule. How to damage
Things from that.
no, that would not damage the smart word, that would just damage the projector. Let's see if that works. So, yes, we are connected. Yes, it might have worked. Oh, then one reason not. Alright. So, what we know how to do is figure out the average rate of change. Alright? Now, what we really want to be able to do is this is the average rate of change between this dot and this dot. So this is what we want to be able to do. We want to first be able to figure out, okay, if we know how to figure out the average speed between this dot and this dot. Alright? We know how to figure out the average rate of change between this dot and this dot.
I don't have to be on there.
Huh?
It's gonna be.
Well, we're putting more than one B. Alright? And then we can figure out the average rate of change between this dot and this dot. I don't know what that is. Hold on, it's wrong. Oh, yeah, that's why, because now it's not lined in.
Oh.
Okay, so forget this. What we're going to be doing here is this. Alright, so alright. Smartboard's not working. Alright. So if we want to find the slope at A, All right, we're going to start by looking at the slope between a point, or between A and a point close to A. All right, so we're going to say we have this point right here. All right, now instead of calling this B, okay, we are going to call this A plus H, where H is the distance, the distance that we added on to A. All right. So again, we're looking at a point. We're looking at the slope between A and a point close to A. So we're gonna call this A plus H. Okay. So what we have here is we have in this case right here. This is right here. This is F of A. And this point right here is F of H. Okay? I'm not F of H, not F of H. F of A plus H. Good. So it's F of A plus H. Now, here's my question. We know we have 2 points up here, right? We have you understand that we're finding the limit, we're finding the average rate of change from this point to this point. So how would you write that? If we were writing that in using the slope formula, what would we have up there? F of A plus H minus F of A divided by A plus H minus A. Alright, all we did is we took our thing of F of B minus F of A divided by B minus A and plugged in the new stuff, what we have from that picture that we just used to make a function, a graph. Alright? So, we don't want to find the average rate of change. We want to find an instantaneous rate of change right here, which means that we don't want this point to be H units away from here. Right? What distance from, if we wanted to figure out the instantaneous rate of change, right? What distance would we need H or A plus H to be away from A? What would H need to be? So the idea, so in that graph we didn't finish drawing, the smartboard is being done. What was happening was we kept finding, all right, points closer and closer and closer and closer. So if we're trying to figure, if we got points closer and closer and closer, what's happening to H? It's becoming smaller. And we're going to keep getting smaller because we don't want points further away. We don't want points that are far away. No, we don't want that point. And we want points that are really, really close. How close do we want to get? So that, wait, what did you say? To that exact point. If we have moved this second point at A plus H all the way to this exact point, what value would H be? No. Think about what you just said. If H is A, it would be A plus A, which would be that one all the way out here. If A and A plus H are the same point, what value would H have? So H is the distance away from A, right? So if you have A plus whatever distance here, good. The distance between A and A plus H has to be 0. You said you want to be the exact point. So in order for A and A plus H to be equal, H has to be 0. Do we know anything about what happens? So this this distance right here, h, is getting closer and closer, it's approaching 0, right? Do we know anything about, are we using anything when we say something approaches 0? The limits. We've been saying the limit as x approaches 0. So what we're going to do here is instead this slope, and we're trying to find the average rate of change, the instantaneous rate of change at a single point. What it's really going to be is not this, but it's going to be the limit as h approaches 0, because h is getting closer and closer to 0, of f of a plus h minus f of a divided by a plus h minus a. Alright? And we can clean this up a little bit. Alright? If you're looking at this, do you see anything that would allow us to sort of clean this up? Meaning simplify this a little bit. Think about, first of all, a minus a is, that those cancel out, right? So this is really, yes, this is really the limit as h approaches 0 of f of a plus h minus f of a divided by h. Now, then you said put 0 in for h. Can we put 0 in for h now? So we can't really put h in for, or we can't put 0 in for h in. Alright, so what you need to understand, if you want to find the instantaneous rate of change, or the slope, at a point, alright, so we said, how do we find the slope of the tangent line? How do we find the slope of the curve at a single point? Alright, how do we find the instantaneous rate of change if you only have one point? The answer to these three questions, right here, is the limit as h approaches 0 of f of a plus h minus f of a all divided by h. That's the answer to those three questions. This is how you find the instantaneous rate of change at a single point. This is how you find, well, yes, that's the answer to those three questions. This is how you find the slope of a tangent line at a point. This is how you find the slope, alright, of the curve at a single point. Okay? So, how do we use this? We want to find the slope of this function. F of x equals x squared plus x at x equals 2. Alright? We want to find the slope at that point. We don't want to find the slope between 2 points. We want to find the slope between, or we want to find the slope at x equals 2. Okay? We know that we use the limit as h approaches 0 of f of a plus h minus f of a divided by h, and that will give us the slope of the that will give us the slope at a point for a given function. So, how do we do this? Well, first of all, okay, we have the point x equals 2, right? So what we have is, we need to find the slope, which n is equal to the limit as x approaches, please work. Stupid
I didn't.
God! Okay, the slope is equal to the limit as h approaches 0 of f of, what is, a is our point. So what point are we looking at?
Okay.
So it's going to be 2 plus h minus f of a, which is 2, divided by h. Okay, so now here's the thing. This takes some math. And I'm gonna preface it with this. You guys do the hard work now to do this. I'm gonna show you a shortcut on how to do this in a couple days. Alright? So
this is not a great idea.
I'm not as customized.
Here's what we do, okay? So we have to, first of all, we're plugging this in. F of 2 plus h means you have 2 plus h squared plus 2 plus h. Alright? Minus,
Why gotta do this weird?
because that's x
Okay.
squared. Alright? Minus f of 2. Well, f of 2 just means plug 2 in for x. So you have, so f of 2 is equal to 2 squared plus 2 is equal to 6. Alright, you have minus 6. That's all divided by h. And I put bad notation here. Okay, I should have the limit as h equals to 0 in front of this. Okay? So it should say equals the limit as h equals to 0. Now, this takes a decent amount of work that you guys have to be willing to put in. Okay? So, what we have, this is equal to the limit as h approaches 0. Alright? 2 plus h squared is going to be 4 plus 4h plus h squared plus 2 plus h minus 6 divided by 8. Alright, so we have this now. So we have, this is equal to the limit with what? All I do is expand the quadratic. So then I have 4 plus 2, that's 6. Minus 6 is 0, so that cancels out. So that cancels out. So then I have 4h plus h, which is 5h plus h squared divided by h. Alright? Well, what do I notice here? I notice that some of these h's cancel out. So this is really equal to the limit as h approaches 0 of 5 plus h. And that h down here at the bottom goes away. Because it cancels out. So now, with it, I can plug 0 in. Just like finding the limit. Alright, if I plug 0 in, it's not going to be undefined or anything. If I plug 0 in, I get 5 plus 0. So the limit as h approaches 0, 5 plus h is equal to 5. But, so, what we're saying here is this. The slope, alright, so m, the slope, so we're saying the slope at x equals 2 is 5. Alright, slope at x equals 2 is 5. Make sense? So, okay, first of all, that bell made me, I need to show you, I'm going to give you guys some homework that involves you doing this, so I'm going to show you an easy way to check your answers. Okay? You can check your answers on the calculator. Alright? So you can do that by, well, I mean, if you can remember, you don't have to. So, alright. So, the way you do this with your calculator is like this. So what is that equation we just did? It's x squared plus x, right? So you just do this. You're going to go one, you just type in the equation. X squared plus x. Alright, so you type in the equation. It's graph. I'm going to do something. 6. So here's my graph. X squared plus x. So what you do here, anytime I want to do something with this graph, anytime I want to calculate something, I'm going to hit second trace. And you're going to go down to where it says number 6, dy dx. The D means, so this is not even, this looks like slope, right here. And we're gonna talk more about this notation. D stands for delta, which is change in y, divided by change in x, which we did, y2 minus y1 equals x2, or over x2 minus x1. So what we do is, we hit that, so we're gonna set 6, and it says, it comes out here, and what x value do we wanna figure out the slope at? So I type in 2, and I hit enter. And it tells me dy dx is equal to 5. Is that or is that not what we decide? So you can do that anything. No matter what the equation is, whatever the function, you type that function in, you hit dy dx, and you get, and it will tell you what, and you type in the point. It will tell you what the slope is at that point. So, now be careful, sis. I'm telling you what your homework is. I told you 84 is 25 to 20, or 25 to 30, and 47 to 50, right? So what you're doing on this next part is, hold on. You guys are doing, yeah, you're doing 90, you're doing 1 through 6, part, page 92, 1 through 6, part A. Oh, we are in this, never mind. Oh, here's what you guys have. You guys don't have homework except for finishing up with on page 84, taking me, I'm not turned in. So you need to make sure you turn in anything you have to turn in this for the past few days. Alright? You guys will, I would say, expect to have a quiz on Monday. Quiz on Monday, okay? What we'll do is we'll review a little bit, like before the quiz, and then we'll take the quiz.